Welcome back. Today we're going to be looking at three-dimensional geometry, and since this is being filmed on March the 14th, or Pi Day 3.14, I'm going to be focusing particularly on three-dimensional shapes centered on the circle. These include, but are not limited to, the sphere, the cone, and the cylinder. All three-dimensional shapes are based upon extensions of ideas included in two-dimensional shapes, but drawn out to not be flat, but to now have a third dimension or elevation. We're going to view 3D shapes as 2D shapes given depth. So all 3D shapes are simply 2D shapes with depth given to them, and this allows us to figure out the property of volume, or the space within a container, as the surface area of one of the bases times the depth of that base, which gives us SAD. If we're dealing with a cylinder, the base is a circle, with the height being, or the depth being, how far apart the two visible circles are. So, just as if you've ever gone shopping, different round cans can be found in different heights and different sizes. They're each going to have different volumes. So, let me correct that spelling. The surface area on the bottom is the base, B-A-S-E, not bass. Okay. So the volume of a cylinder is found by pi times r squared, the area of its circle, times the depth of the circle. In this case, we can make our radius 1 inch, or 25 millimeters, and our depth is going to be 75 millimeters. And when we plug this into our calculator, pi times 25 millimeters squared times 75 gives us a volume of 147,262.1556 millimeters cubed, where a cubic volume is made up of cubes, which are tall boxes where all three perpendicular dimensions, or all three sides emanating from one point on our cube, are the same length. So this volume could be determined to need this many 1 millimeter by 1 millimeter by 1 millimeter cubes. Any cylinder can have its volume determined using the same formula. What happens if the cylinder doesn't stay this uniform in its width the entire time, but instead contracts down? Okay. We have a cone. So we want to find the volume of a cone, and this is going to be 1/3 times the pi times r squared of the base times the depth. And anytime you have something start out with a wide base and taper up to a point, the volume is only going to be 1/3 of its original size that you would expect if it was the shape of a cylinder or a box. So our base again is 25 millimeters. Our height is still 3 inches or 75 millimeters. So we're going to take our original value or previous value and divide it by 3, or we can do this calculation again and we get that this is 49,087.385 cubic millimeters. A cylinder, like a scoop of ice cream that can go in our cone, has its own formula for volume as well. And that formula is 4/3 times pi times r cubed. Our radius here is still 25 millimeters. So we have 25 raised to the 3rd power times pi times 4 divided by 3 gives us a volume of 65,449.847 cubic millimeters for our sphere. Our sphere is the same diameter as our cylinder, but it narrows. It starts out with 0 width, expands at its center line to our equator to have a full width, and narrows back down. So these are three-dimensional shapes based on, or the volume of them based, or when we have any three-dimensional shape is going to have at least one, if not multiple surfaces, and the surface area of a 3D shape is the sum of the areas of each side, or of each face. A sphere has only one face, a cone has 2, and a cylinder has 3. A cube has how many? That's right, 6. A pyramid, similar to those built in Egypt, has 5 faces. We'll take a look at how to figure out the surface area of that in a moment. But we want to do the surface area of a sphere first. And that is going to be 4 times our value of pi times the radius squared. So using a radius of 2.5 millimeters and squaring that, 25 squared times pi times 4 gives us 7,853.8 0.982 cubic millimeters. So the surface area of this sphere is 7,853 cubic millimeters. Now we want to figure out the surface area of a cone. That is going to be found by two parts because we have two faces. We have our base, the opening that you can put your ice cream in, and our smooth side, found by pi times r times the square root of r squared plus h squared. And if we were to take a triangle and figure out the area that would be marked out when we spin it by the green side, that side, or the hypotenuse of this right triangle, is the outer edge of our cone, or gives us the outer edge of our cone. So we have a radius of 25 millimeters, a radius of 25 millimeters, square root of 25 squared, and our height is 75, and we're going to square that. Now we need to be careful with our order of operations. We need to figure out pi times r squared. 25 squared times pi gives us 1,963.495 square millimeters. We're going to add to that pi times 25 squared times the square root of 25 squared plus 75 squared, and we get 155,227.942 millimeters squared. For a total area of our cone of 157,191 square millimeters. Our first step in solving the right side is inside our grouping symbols. We have 25 squared plus 75 squared. We need to find that 25 squared is 625. 75 squared is 5,625. When we add those two numbers together, we get 6,250. The square root of that answer is just over 79, which we multiply against 625 times pi, and that's how we arrive at the 155,000. So the surface area of this cone is 157,191 square millimeters. And we want to figure out the area of the surface area of this cylinder. The surface area of a cylinder is, we have two circular faces. going to be 2 times pi times r squared, plus we need to figure out how to determine the surface area of the side, or where the label would be. And that length around, or that is dictated by the length around, which is going to be our circumference. So 2 pi times r times the depth. So we have 2 times pi, our radius is still 25 millimeters, plus 2 times our pi times our radius of 25 millimeters, times our depth of 75 millimeters, gives us these measurements to be multiplied together. So 2 times pi times 25 squared, plus 2 times pi times 25 times 75 gives us 124,000, sorry, 12,114.25 square millimeters is the surface area of this cylinder. Okay. Figures based on squares and hexagons have similar approaches that we need to take to find their surface areas, with a hexagon being a little bit more complicated, and they will be included in the second installment of three-dimensional geometry.